Hi everyone. Today we are talking about differentiability. All right, differentiability really just means can we take the derivative of the function? All right, this is going to be a super important concept. So differentiability, like I said, means can we actually take the derivative? So a function is differentiable at a particular x value if the derivative of the function exists or is defined at that x value. So we're going to talk a little bit more about what I actually mean by that. So remember when we did continuity and we had to look at the left limit, the right limit, and the function value to decide if a limit actually to decide if the function was actually continuous or not. So in order to decide if it's differentiable, we have to actually look at the left derivative and the right derivative. And they have to equal each other. All right, so just like for a limit to exist, the left and right have to equal each other. For a derivative to exist, the left and the right have to equal each other. Okay, functions are differentiable unless one of the following characteristics occurs. So this first one that we're going to look at is this very sharp turn here, which we actually call a corner. Okay, in this particular example, this corner is occurring at x equals 0. So we would say that this function is not differentiable at x equals 0. But let's look at why that actually happens. So if we look at the derivative on the left, we know that a derivative is a slope. So if we're looking at the absolute value of x, the slope of this line is actually just -1. All right, which means that the derivative from the left is -1. When we look at the other side then, the slope of this line is actually +1, which means that the derivative on the right side is +1. Since those derivatives do not equal each other, the derivative at 0 doesn't actually exist. Okay, so that's what we mean when we say it's not differentiable. The left and the right limits don't actually equal each other. So types of functions where this can occur, clearly absolute value functions, because that's the one we have. And the other place that this can occur a lot is with piecewise functions. Depending on what your pieces are, they might create a corner at a specific point. Okay? The next one, you guys might even be able to tell without doing much, but the next time where a function is not differentiable would be if there is a discontinuity. All right, this particular discontinuity is a jump, because on the left we're at +2 and on the right we are at +1. So there is a jump discontinuity. But we have to remember that there are other types of discontinuities. There could be removable. So there's a hole maybe. There could be infinite discontinuities, so vertical asymptotes. Or there could be oscillating discontinuities. Excuse me. So any of these four problems that cause a discontinuity make a function not differentiable. All right, in this case, if we were looking at this particular one, the discontinuity would be at x equals 1. So we would say this function is not differentiable at x equals 1. Types of functions where we can have discontinuities would be rational functions, because that's where we could have a removable or an infinite discontinuity, or a piecewise function, because we could have a jump or a removable or an infinite actually. Okay? The third one down here is very similar to a corner, but if you notice, it's actually curved instead of this straight corner in. So this curved part here is actually called a cusp. All right, and the reason it's different from a corner is because if we actually started to look at the slopes of the derivatives here, it becomes almost vertical in the center there. All right, we can write that. It's almost a vertical tangent. Not quite, but almost, and they kind of curve in towards each other. So that's what we call a cusp, okay? Now, cusps occur anytime, well, not anytime, but they only occur when we have rational exponents. So for example, if we had a function like x to the 2/3, that would create a cusp on our graph. And so in this case, we would say that this function is not differentiable at x equals 0 because there is a cusp. Okay? The last type that we're going to talk about here is actually a vertical tangent. When we look at this spot here and we draw the tangent line to the curve, we can see that that's actually a vertical tangent. So the reason that it's not differentiable here is because the slope of the tangent here, the derivative, is actually undefined because it's a vertical line. So the slope of a vertical line, we know we can't find it. It's undefined. All right, so in this case, the vertical tangent would be at x equals 0. So that makes this function not differentiable at x equals 0. Now, this also happens in rational exponential functions, or rational functions with rational exponents. Wow, I cannot talk. I'm so sorry. So this could be something like maybe f of x equals x to the 1/3. All right, and that gives us our vertical tangent. Now there's something that I want to point out to you guys as we look at these 4 different examples. In example 1, I need a different color, sorry. In example 1, this function is continuous. This is one smooth piece. As we look at the limits from left and right, and we look at the function value, they're all equal to each other. So this function was continuous. This function down here was also continuous. And the last one was continuous as well. So when we look at these 3, they were not differentiable at all points. So they had a point where they were not differentiable, but they were still continuous. This function here, it was discontinuous at this point, and so it was not differentiable at that point. But this is going to be really important because continuity and differentiability are related to each other. So that's going to bring us to the bottom here. This is going to be super important. If a function is differentiable, so that means we can take the derivative. Then it must also be continuous. So anytime I tell you that a function is differentiable, you know then that that function is continuous. However, just because a function is continuous does not necessarily mean that it is differentiable. So take a look again at examples 1, 3, and 4. Those functions were continuous functions. We can draw them without picking up our pen. There were no problems there. However, they were not differentiable at one point on each of them. All right, so just because it's continuous doesn't mean you can say it's differentiable. However, if it's differentiable, you can say that it's continuous. All right, so you have to be careful about which one you're talking about. So let's look at what some examples might actually look like here for us, okay? Identify the x values where the function is not differentiable. Explain why the function is not differentiable at those values. So the first place that I see a problem, and hopefully you do too, is here at x equals -2. All right, at x equals -2, we can clearly see that there is a discontinuity. So that is why it is not differentiable at -2. Oops, not diff. I was going to say differentiable. It is discontinuous. All right, and we know that that discontinuity can be classified, wow, I really can't function here, guys, as an infinite discontinuity. Whew, that took a lot of strength, guys. I am so sorry. So, -2, we have a discontinuity, and it is an infinite discontinuity. The next place that I see a problem is this curve right here going on. All right, at x equals -1, there is a cusp. At x equals 0, we notice that the function goes very vertical right here. All right, so at x equals 0, there is a vertical tangent. And then the last place that I notice the problem is at x equals 2. There is a discontinuity there. And that particular discontinuity, it's a hole, so it's removable. All right, so anytime you're looking at a graph, those are the things you're looking for. Either an infinite discontinuity or a removable discontinuity or a jump discontinuity, a cusp, a vertical tangent, or the other option is a corner. Okay, but let's look at more like what kind of examples are going to be on the AP test. Okay, so the function f of x is given by the following: f of x equals x squared for x less than or equal to 0, and 2x for x greater than 0. The first part of this question asks you to determine whether f of x is continuous or not at x equals 0. In order to do this, we're going to have to kind of jump back to what it means to be continuous. So it's a little bit of a review, and it's a nice place to throw this review in so that we remember for the whole year, because you're going to need it all the time. In order for a function to be continuous, we know that the limit as x approaches 0 from the left of f of x is going to have to equal the limit as x approaches 0 from the right of f of x, which is going to have to equal the function value at 0. All right, and that's because we're doing this at x equals 0. So the left limit has to equal the right limit, which has to equal the function value. So hopefully you guys remember doing this in chapter 2, I believe it was. All right, so limit as x approaches 0 from the left means we're looking at x as less than or equal to 0. So x squared, which means the limit from the left is equal to 0. The limit as x approaches 0 from the right means we're greater than 0, so we're plugging it into 2x. So in this case, that limit is also 0. And then f of 0 means where is x equal to 0? So it's equal to 0 in the x squared portion of the graph, which means it is also 0. And since all three of those pieces equal each other, we are able to say that yes, f of x is continuous at x equals 0. Okay? Now, the second part of this question says determine whether f of x is or is not differentiable at x equals 0. So we're going to do a process that's actually very similar. All right, if you remember, I told you that in order for it to be differentiable, the derivative from the left has to equal the derivative from the right. So we're going to see what that actually looks like, okay? Taking the derivative of the left side means when x is less than or equal to 0, we're going to take the derivative of that function. So in this case, that derivative is 2x. All right, the derivative on the right means take the derivative when x is greater than 0. So that function is 2x, which means the derivative on the right side is actually just 2. All right, now they're telling us to evaluate it when x is equal to 0, which means if I do that, I'm going to plug in 0 for x, and I'm trying to figure out if these are actually equal to each other or not. But the derivative on the right is just 2, no matter what the value is. And on the left, I got that it's 0, which means my derivative on the left is 0, and my derivative on the right is equal to 2. And those do not equal each other, which means the left derivative and the right derivative are not equal, which tells me that f of x is not differentiable at x equals 0. All right, so this is an example where it is continuous. We were able to show that the left limit equals the right limit, which equals the function value, but the left and right derivatives do not equal each other, which means that it is not differentiable. And I bet if we were to graph that, we could see that that is the case. All right, we've got a parabola on one side and we've got a line on the other, which means even if we did just a quick sketch, a parabola is going to curve up like this, and a line is going to shoot straight up like this. And so we can clearly see that there's a problem going on there and that the derivative does not exist at x equals 0. Okay, we're going to do 2 more examples. I'm going to move through them a little bit quicker because this video is getting really long. I'm sorry. Actually, you know what? We're going to skip question 3. We're going to do it together in class. But we're going to go to question 4 really quick. So let f be the function defined below where c and d are constants. Actually, I lied and I changed my mind. We're going to do question 4 together in class. I know, I'm sorry, I'm jumping all over the place. We're going to do question 3 because it's short, okay? So determine whether f of x is continuous or not. And actually, we're not doing f, we're doing g. So change that to a g for me, please. All right, so we're going to do the limit as x approaches 1 from the left of g of x, the limit as x approaches 1 from the right of g of x, and then we're going to do g of 1. All right, our left limit means we're plugging it into x squared, so we would get 1. The right limit means we're plugging it into 2x, so we would get 2. And then g of 1 means plug it in where x equals 1, so that would be 1. And we can tell actually even just from that first part that not all 3 pieces are equal, which tells us that g of x is not continuous at x equals 1. All right, which means that in this piecewise function, there's got to be a jump. All right, on one side it's 1 and on the other side it's 2. So it is not continuous. The next question asks if it is differentiable at x equals 1. Well, in order for a function to be differentiable, it has to be continuous. So since we already decided that g of x is not continuous at x equals 1, g of x is not differentiable at x equals 1. And we don't even have to check anything, okay? Because if it's not continuous, then it can't be differentiable, right? One of our reasons that we said it might not be differentiable is because of a discontinuity. Well, if it's not continuous, it has a discontinuity, so it cannot be differentiable. All right, we are going to do example 4 together. I'm really sorry that this was a much longer video, but I'll answer any questions you guys have in class. I'll see you later. Bye.